today our agenda would primarily be to go through DQ theory first. I have these two links which I'll open up on my tab and like I'll share it on the chat also. Then we'll discuss how to solve the sliding window range max in order in. So because of the voting, I got the idea that like most of the people are interested in covering DQ theory. And like the second most prominent thing that came out of the voting for the theory topics was discussing Z-theory rectangles. I think Aryan discussed it briefly in like the last session also, but I think like this is the most classic use case of the week's content, which is stacks. Like then coding Z-theory rectangles will be optional. I'll just ask you guys if you think we should or not, and then we'll discuss Z-theory 1202, and I think we should code this one out because like the STL usage in this question is actually pretty good. Yeah, that's pretty much the agenda. So starting off, I'll like share these two links. This is the first link for DQ, and this is the second link. I hope everyone can hear me now, loud and clear. All right. So if we go through the first link, it's basically how DQ is used. So DQ stands for doubly-ended queue. You can see here, right? That's the full form of DQ. Doubly-ended queue means a kind of data structure in which you can push and pop from both the ends of the data structure, like from the front also and from the back also. So it's kind of like you can say it's, yeah, like doubly-ended queue literally means that it acts as a queue from both the ends. So the main functions that you'll probably care about is size, operator, which is basically accessing an element, push back, push front, pop back, pop front. And dot front and dot back just gives you the topmost element or the last element. Yeah, see here. Dot front and dot back just gives you the access to the first or the last element. When you do push back or push front, you're basically pushing an element either at the back or at the front. And whenever you're doing pop back or pop front, you're popping an element from either end. The interesting thing is that, okay, so if you think about it, how you would go about implementing a doubly-ended queue would be that you use some kind of doubly linked list, and then you'll be able to get all these functionalities, right? Push back, push front, pop back, pop front. But you still won't be able to get operator access. Like you can't access any random element in O1 in a doubly linked list. But in DQ, you can do that. So in DQ, if you go at operator and you see, so what it does is basically what we generally use, like my DQI, you can access any element. It need not be the front or the last, which you can't do in stacks or queues. You can't access the second element in stack easily. Like you'll have to pop the top and then access it. But in DQ, you can. And the interesting thing is here, the complexity is set to be constant. So it's like the C++ library says that it's O1. The magical thing is, if you try to implement it using a doubly linked list, you can't get O1. So that's where the second link that I shared comes in play. If you want to understand like the broad idea of how doubly-ended queue is implemented by C++, then like they cover it in this question. In like this is a Stack Overflow question. It basically says that how is the cost of inserting element, like how is the cost of accessing elements constant time, whereas in English it should actually be order n. So like this is the idea. You can go through it. We don't really need this use case, but just know that in C++, if you access a random element from a DQ, it's order 1. It's a slow order 1. So if you use a DQ versus a vector for the very same question where you don't actually have the benefits of DQ, then it will be slightly slower. But nevertheless, it's order 1. Okay, any doubts in like the DQ library? Like you can see here, I think you can use the size, and yeah, he doesn't use pushback or push front in this sample code, but yeah, in general you can. Let me show some example where he actually uses the pushback and push front. Like those are the important. Yeah, so my DQ.pushback. It's identical syntax to say queue or a stack. It's just there are 4 functions here: pushback, push front, pop back, pop front, and dot front, dot back. All right. If you have any doubts, just put them on the chat. Okay, so the second thing we wanted to cover was like a question tackling DQs. Like, so like this is the TLDR version. Queues are generally used only for BFS. That's the like most prominent use case of queues. That's doing a BFS. Stacks are used for bracket questions or DFS or avoiding recursion limit. Like, I don't think you can find any other use case of BFS easily. And also stacks are used for the fourth thing that I covered there: bracketing, DFS, avoid recursion limit, and what was the fourth thing? Yeah, in that's your rectangle. So yeah, we'll come about that's your rectangle later. And DQs are generally like most commonly used for sliding window, range max in ON. Like when you have to do the sliding window range max question in ON. So I'll explain the question now. The question is, you're given an array. Let's say the array is, I'm just creating an arbitrary array. Okay. And let's say K is 3. K is 3, that means, so your answer array should be the max of the first 3 elements. So the max of these 3 guys, which is 7. Then the max of the next 3 guys, like from second element onwards, I'm assuming 1 based indexing. So the answer is like the range max of all 3 consecutive bunches. So for the first thing, it's 5, 7, 3, like max of all 3, which is 7. The next thing is 7, 3, 4. So the max is again 7. The next is 3, 4, 10. So the max is 10. The next is 4, 10, 6. The max is again 10. The next is 10, 6, 9. The max is again 10. The next is 6, 9, 8. The max is 9. The next is 9, 8, 2. The max is 9. So you actually have to print this answer array. Like that's the objective of the question. And you have to do it in, okay. So doing this question in order NK is trivial, right? Like just like slide, like pick every window and just do an order K to find the max of that window. And then just shift by 1 position, do an order K max of the window. Right? Does anyone have any doubts regarding the order NK trivial solution? But if K is large, then obviously order NK can go to order n square in worst case, like when K is almost equal to n. Or like, let's say K is n by 2 or something. So you have enough answers to print. Okay, the actual complexity is more precisely order n minus K times K. This is because you only have n minus K windows of size K. So this comes out to be order nk minus K square. And you can maximize it by putting K as n by 2. Then this will come out to be n square by 4. So in worst case, you can have n square by 4 steps in the like most trivial algorithm. Okay. So now the issue is that how do we improve this? So we improve this using a DQ. So on this array itself, let's try to work. Give me a moment. So we want to reach complexity order n. Okay. Yep. So the idea is, let's say you have a DQ. Let's name the DQ as D. Okay. And when 5 comes in, so whenever an element comes in, we push it back. So we want to maintain this invariant. So invariant in maths is known as a property that you want to maintain throughout the problem. It's heavily used in like discrete maths courses, like discrete maths, discrete structures. The idea is that there is some property in the problem that you want to maintain throughout your algorithm. Okay. There is some property that you want to keep preserved throughout the algorithm. So here the invariant that we want is that DQ should be decreasing. What I mean by this is that the first element should be bigger than the second element and so on. That is, D1 should be greater equal D2, which should be greater equal D3, and so on. We want this property to be maintained always. Okay. And what we are going to insert in DQ is pairs. Okay. But for now, just think of them as like the elements themselves. So let's say first we insert 5. And we'll insert elements from the back. So we'll do a push back to insert elements in the DQ. So first we insert 5. Then, okay, since case 3, the first 3 insertions have to be done forcefully. So first we insert 5. Then when we are inserting 7, we'll realize that we want to maintain this invariant of ours. So to maintain the invariant, what we'll do is, before inserting 7, we will pop out 5. The reason for popping out 5 is because once we have seen the 7, we know 5 can never be the answer. Like 5 can never contribute because the 7 is immediately next to it. So in whichever window 5 will come, 7 will also come because 7 is to the right of it. Okay, so Devansh is asking what is invariant. Invariant is a property, like invariant is an English word, basically it's used in maths a lot. It's a property that you want to preserve, that you want to keep in some sense throughout the algorithm. Throughout the algorithm. It's something like you want it to stay true throughout the algorithm. Okay, cool. So in DQ, when you inserted the first element, you pushed back at 5, then you saw 7. Now you'll pop out 5. So the way you'll pop out is using pop back. Okay. And once 5 is popped out, you can push 7 in. So now there's only a 7 in the thing. The intuition for popping out 5 was that since we've seen a 7 after 5, we know that every window that will constitute of 7, like every window that will have 7 will definitely have the 5. Sorry, vice versa. Every window that will have the 5 will definitely have the 7. And since we know 7 is bigger than 5, so we might as well discard 5 because we know 5 will never become the answer. Like the 7 is always to the right of it. Whenever you slide the window, 7 will still come if 5 is coming. And so 5 is never the answer. So once we've inserted 7, then we insert 3. Since we have to maintain the invariant, we don't do anything. We just let 3 be inserted. Sorry, my phone ran. Yeah. So now after inserting 3, yep, let's move forward. Didn't understand the first point. Oh, okay. So I first inserted 5, right? And then I inserted 7. When I was inserting 7, I had to pop out 5. Like, let's not get into the detail of 5. I was popping out 5. I'll explain it later also. More like this example is pretty long, so you'll probably get this. Okay, this is not a question instead. This is theory. And like we are trying to cover this question that you have an array, you have 3 elements, and you have to answer the maximum of every subarray of size 3 in order n. So first we inserted 5, then we popped out, then we inserted 7, then we inserted 3. Now when we are inserting 4, we'll again try to use the pushback, but we have to maintain the invariant. We'll always have to keep in mind that we have to maintain the invariant. So to maintain the invariant, we'll have to pop out 3 because just putting in 4 is like we broke the invariant because now 7 is greater than 3, but 3 is not greater than 4. This thing is getting broken, right? So to avoid getting things broken, we pop out 3 and then insert 4. Right? And we'll keep on doing this. So we know how to push elements from the right, basically how to extend this window. So it's a sliding window algorithm. The intuition of every sliding window algorithm is that you have a L pointer and you have a R pointer. You have a method to expand the R pointer to the right, that is to include new elements. And you have a method to pop out elements from the left. You should have both these things. And then it works out. So before inserting 4, actually, what we wanted was to get the answer. Like, sorry, here was a 3, right? And now we want to get the answer. What is the answer for the first 3 elements? So the answer will be just access the front. So that's saying access d dot front and try to see what value does d dot front have. So here d dot front has 7. So our answer is 7. Okay. Right now this was a simple case, but let's move forward. I'll show you like slightly tricky case that will come here. When we inserted 4, this gate popped out and we inserted 4, right? So now the window we are trying to question is this window, right? 734. And we'll again see the d dot front to get our answer, which is 7 again. So we'll just have 7 in our answer. Now we'll try to insert 10. Okay. Yes. Okay, for the sake of simplicity, I'm changing the example slightly. let's say the next element was smaller, 2 something, okay? And yeah, I'm changing the example slightly just so for the sake of simplicity and so that you can see every case that comes up. So now when we're inserting 2, it'll come up here, right? And we won't pop out anything because our invariant is maintained. That is 7 is greater than 4, 4 is greater than 2. So we like 4 doesn't need to be popped out when we are inserting 2, right? The issue is now, if you try to access d dot front, you'll still see 7, but 7 is not actually the answer because it got kicked out, because the window that we are actually looking for is 342 and 7 is not in the window. So the way this works out is you actually need to have a pair. So, okay, the issue here is that we still think that 7 is inside our range. We need to update our data structure to know that 7 is not in our range anymore. So the way it works out is you actually keep a pair of element comma indice. So here, instead of 5, you should have kept 5 comma 1. That is the 5th element and the index is 1. Here, instead of 7, you should have kept 7 comma 2. That is the 7th element with second index. So 7, 8, 4, 5, D6, F6 is asking how we are maintaining the invariant. The way we are maintaining the invariant is that whenever we push elements at the back, we use the pop back method before that and pop out some elements. So let's say our DQ right now looks like this: 10, 8, 4, 2. And let's say we are inserting, the next element we are inserting is 5. Okay, inserting 5. What we'll do is we'll pop out 2 and 4. Like we'll access the back, we'll pop 2, then we'll pop 4. We won't pop 8 because we don't need to. And then we can simply insert 5 after popping out 2 and 4. Does everyone get this? Like how we are maintaining the invariant. Yeah. And like 784 just messaged me privately the question, but like, yeah, you can post all the questions at like public so that everyone can see them on the chat. So yeah, that's how you maintain the invariant. And the second thing I was explaining was that you need to keep the indices. Why you need to keep the indices? Because in our case, the issue that came up was, so let's say you have all the indices, like 3 has the indice 3, 4 has the indice 4, 2 has the indice 5. Okay, because like this is the first index, the second index, the third index, the fourth index, the fifth index, right? Now, okay, 5 1 was deleted, right? 3 3 was deleted. Now you had this thing, right? 7 2 4 4 2 5. Like these are pairs, 3 pairs you had in DQ, and you accessed the front. Now, when you look at the front, the window you're considering right now was 3 4 2. That is, L was 3, R was 5. You were starting at the third element and you were ending at the fifth element, right? But 7 2 shows you that the head of the queue right now is the second element. And so in a timeline perspective, you can think that this is the third element, this is the fifth element, and the queue right now has second element at the front. So you can pop this element. So what I'm trying to say is that if your DQ has something comma something, okay, it had this thing 7 2, then it had 4 4, and then it had 2 5, right? And you wanted 2, and your L was 3, R was 5. That means you are trying to get the max of the AL to AR window. Then when you see the front, you see 7 2, you should pop it out. And by popping, I mean here, you're doing pop underscore front, because you're accessing the front and popping it out. You're popping this because this is an old element. This is not actually present in the range anymore. So we are still maintaining the invariant that 7 is bigger than 4, which is bigger than 2. That these three things are decreasing. We are still maintaining that invariant. We never break that invariant. So always think from that angle. And we are popping this element out because we know that this element is now never useful. Like when we stretch, in the next iteration, we'll stretch it to L4, R6. Still, the second element won't be useful, right? Because it's been like, it's out of the window already, and we are moving our window to the right. And this is an element to the left, which is discarded already. So you need to pop this out. And okay, so another example could be, let's say you had 8 1, 7 2, 4 4, 2 5, What this means is your array looks something like this: 8, 7, 1, 4, 2. If you had an array like this, your DQ will probably look like this, what I'm showing you right now. Right? You can run through it like, yeah, on paper pen. And this will how it will look like. Because one will get popped out like from here. Now here, let's say your L is 3, R is 5. Then again, you need to pop out this thing and this thing, both these things, because both these things, the indice of these things does not lie in the range of 3 to 5. Like 1 doesn't lie in 3 to 5 and 2 doesn't lie in 3 to 5, but the next two guys do lie. So our answer would actually be 4. Like after popping these two guys out, we'll say 4 is our answer because this thing lies in our range. Is the broad pseudocode like all right with everyone? So we have this method like push an element into DQ, where what we do is we say, okay, I'll go through the code on the editor actually. That will be much more comfortable and like, you guys can actually see what's happening. But the broad idea that you have to maintain this invariant. I think like this is the key property in remembering this algorithm and how it works. How do we use DQ to get sub arrays max? Yeah, in OM. So you have a size fixed K, and like you have to find for every subarray of size K, you have to find the max of those guys. That's the question. So this was the invariant that we were maintaining, and I'll show you the code now. Yes. Okay, I can't. Stop share. Yep, share screen. Cool. Okay, got it. Yep. So I'll just share. Like let's name it dq.cpp. Okay. I hope like in case the screen is not visible clearly, I changed my layout from last time because that was black, and in YouTube streaming it looked like in streaming it looks pretty pathetic. It's very hard to read stuff from a black editor. I hope this is much clear, and in case you want me to increase the font size or anything, just let me know. So our question was, we had an N and K, right? We are taking in both, and array also. Right? And then we have to print our answer array. So the way we will work this out is, okay, let's say we have this DQ of pair intent DQ. Okay. And here I'm using pair intent. So like since in week 2 only we introduced everything, like will it works in multiple queries as we are deleting some elements? I don't get the question of Yashraj exactly, but yeah. So we are in order n, we are basically trying to cover every subarray of size K, because it was a sliding window algorithm. So the idea of sliding window algorithms is that you have L equal, initially you have L equal 1, R equal K. In next iteration, you have L equal 2, R equal K plus 1, and so on. So eventually it will be something like N minus K minus plus 1 and R equal N. And for each of them, you know the answer. You know the answer, you know the answer. This will be answer 1, this will be answer 2, and so on. This will be answer, I think, N minus K plus 1. Right? And like recovering the entire answer array takes you order. That's our idea. So we have this DQ structure in which we have a pair inside. The idea of the pair was that in the second element of the pair, we want to keep the indice. What index does that element have? So we'll have some function like push, let's say, and we're just pushing in, let's say that's it. That's our function. Okay. How we'll define that function is, what is the point of declaring and what does it mean? Okay. Good question. I mean, so, okay. For most CP questions, comparative programming questions, the default, like if the problem is meant to be solved in order n, a lot of people give you the constraint as n less than equal 1e5. That's how just like problem setters generally do. So by default, I set it to order 1e5 plus 5. I could have set it to like 100 or something. Like it wouldn't have mattered, but it doesn't matter if I'm setting it to order. Yeah, and okay, 1e5 actually means 10 to the power 5. So I'm actually setting it to this value. Okay, 1e5 is the scientific notation of 10 to the power 5, which means 10 and how many zeros after that. So 5 denotes how many zeros after that. If you do this like this, then it means this thing. Yeah, 10 to the power 5 is 1. No, not really, Sean. It's more like this is equal to 1.5. Yeah, and when I'm adding 5 here, that was implying. Yeah. So you can just Google up scientific notation. It's like, that's okay. It's more like a concise version of writing thing. So in case you actually manually write down the zeros, sometimes the issue is that you mistype. You by mistake typed 1 0 less or 1 0 more. So this is a more easier way of not making that mistake, that you by mistake type more zeros or less zeros. Otherwise you have to manually like eyeball and see how many zeros you've typed. So we have this void push function and we are pushing in the xth element. Okay. So the way it will work is, while the DQ is not empty, if DQ dot back dot first is less than DQ dot back dot AX, then we'll do DQ dot pop back. Okay, so in most of the like linear data structure questions, whenever you're doing some push or pop operation, which involves popping a lot of elements. So here I'm popping a lot of elements, like more than one element. I'm popping back, popping back, popping back. The condition generally is that you do that till the time the thing doesn't go empty. So here I'm saying till the time the DQ is not empty, this means DQ is not empty. Till the time the DQ is not empty, run this thing, which is saying if the back of the DQ, let's say the DQ right now looks like this, 8,1, 7,2, 4,3. Okay, Swagat, the question that's going on is a theory question, and it was mentioned in the theory discussion, like the topmost voted question, which is basically how to calculate every subarray max for every subarray of size k in ON. Yeah. Okay. So let's say the DQ is this, and let's say x being like x is obviously 4, ax, I'm sorry, ax is equal to, let's see, what will you want? Okay, let's say this is 10, and we are inserting 9,4. Okay, so we are inserting, let's say 9,4. Now when we are inserting 9,4, what will happen? We'll pop out 4,3 and we'll pop out 7,2, right? We want to pop out these two elements because we want to maintain the like let me put this like this. We want our new DQ to look like this, right? After the insertion step, we want it to look like this, right? Afterwards, like at the next step, after this thing runs, after the entire push function gets evaluated, after the push function gets evaluated, we want our DQ to look like this, right? That is 7,2 and 4,3 are popped out. So the way it works is we access the back of the queue, which is 4,3. We check the first element, which is 4, the element itself, and compare it with AX, which is 9. So we are comparing 4 with 9. 4 is less than 9, so we pop. So now after this pop, after the first iteration, what does the DQ look? It looks like 10,1, 7,2. That's it. 4,3 just got popped out, right? Then we again go and we see, is the DQ empty? No, it's not empty. So we go inside, we see DQ.back.first, which is 9, sorry, which is 7, right? Here, like the last element is 7, right? And we compare it against 9. So we again pop out. And now the DQ looks like 10,1. That's it, right? Now we again go into the while loop. It's still not empty. We check this condition again. Now it's asking 10 less than 9. False. So we go inside the else and we break. Does everyone get this? Because 10 is not less than 9, so we break out. After breaking out, is back the back part of the queue and first the first part of the queue? Oh, sorry. Okay, nice question actually. Sorry, I should have explained this. So dq.back just gives you a pair. dq.back gives you a pair, which basically refers to the last element of the DQ, which you are correct in saying that in the, like, let's say the DQ was 10, 1, 7, 2, 4, 3, like these three pairs, then it would have returned 4, 3. Dot first is the pair's first element. Like here, if I just do this, I'll get a pair. Like this dq.back will return a pair, but I want the first element of the pair. By first element, I mean, in this case, when the dq.back gives you 4, 3, I want the 4 out of the 4, 3. So if you read about pairs, like how are pairs accessed and used, then you see that dot first is actually used to access the elements of the pair. So like this dot first actually refers to accessing an element of the pair. Yeah. And it's actually dq.back and dq.front. Like the complement function is actually dq.front. You don't use first anywhere else. You only use it for pairs. Back will return the last element. Yes, back will return the last element. So, okay. Afterwards, like after all the popping, what do we have here? When we break out, we have 10 and 1, right? Can't we use square root decomposition? Then also the time complexity would be nk. Okay, AKS. So in this question, we are actually trying to get something better than nk. We are actually trying to get an on. You can see at the top. Obviously, like you might be correct that in square root decomposition we can get an nk. Like the classic trivial algorithm is also nk, but we're trying to get an on. Yeah. So after 10, 1, we'll have to insert 9, 4 again. Like up till this point, we have just ensured that we have popped out all the elements required, right? We have popped out all the elements required. So this array 10, 1, 7, 2, 4, 3 here, this array now just has 10, 1. Now the next step will be to dq pushback and actually insert ax, x. Okay, so this is also a syntax thing. In C++ 11 and like all the modern C++ versions, you can insert or like make a pair using curly braces. So just put something like a comma b inside a curly brace, and then this thing is a pair, and you can insert that pair inside. So here, my pair's first element is ax, which is what the thing that I was trying to insert, right? Like ith indice, I'm trying to insert the ith indice. So here, x is actually position of the index. X is equal to position of the element which we are trying to insert, right? So ax and x is the position itself, which we want at the second thing, right? Okay, notice that in the push function, we actually didn't ever use the second element of the pair, but that doesn't mean it's not useful. We'll see it later. So after this, we'll want to query. Okay, so now we've inserted the first k elements. Now what do we want to do? We want to run a loop from k plus 1 to n. In every loop, we want to first query the range from I minus k minus 1 to I minus 1. Okay, or you can just say, like first we are querying from 1 to k. Okay, then we are pushing in I, and then we are querying from, okay, let me be, like I want you guys to actually get the feel of what I'm trying to do. So let's make it like this. I mean, there are multiple ways to write this thing. I just want to write it in the way that most people understand what's happening. Okay. Yeah. We also first construct the entire DQ shoot. Yes. Okay, no, not really. So we first inserted only the first k elements inside the DQ. You can see here, we only inserted the first k elements. Then as in, so it's like a sliding window algorithm, and the will this session be available on YouTube Live after the live stream is over? I think so, yes, Kaushal. I'm not 100% sure, but I think Pallavi said that, yeah, it will be there. So yeah, the question that Shruti was asking, we are constructing the DQ on the go. So you can see that here also I'm pushing in elements. I'm pushing in the R again and again. So initially I inserted the first k elements because at least I need those k elements to be present inside. Then I printed out the answer for those first k elements. So let's say here it was C out this thing. And then I pushed in the k plus 1th element. Then I printed out the answer for the range ending at k plus 1th element. And then I pushed in k plus 2 element, k plus 2th element. And then I printed out the answer of the range ending at k plus 2th element. So it's a sliding window. When I use the word sliding window, it means that L and R are both being incremented one by one. Tuck, 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 tuck. Here you can see L is 1, R is k. In the next iteration here, it will be L is 2, R is k plus 1. In the next iteration, it will be L is 3, R is k plus 2, and so on. So every time when this is happening, like just an R is being incremented by 1 and we are pushing it again and again inside. All right. So now we need to define the query function. Okay. And the idea is this: while the DQ is not empty, why are you pushing the index I and not the value in AI? Okay, so just my push syntax looks like this. Like I just pass in the indice and not the value because, so I'm pushing in here X, right? But it's the position, but I actually access the value also. Here I'm accessing the A of X, or here I'm accessing the A of X. So it's not like I'm not accessing the A of I. I am accessing the A of I inside my push code. So Vishnu, like, yeah, you could have passed AR, comma R if you wanted. Like you could have had a syntax like this also. Like, but this is just more, I think, concise. Yeah. So here, till the time the DQ is not empty, what we are trying to do is, okay, initially our trivial thought process was that we can just return the front, right? And the front's first element to be precise. If we had done this, this was our trivial idea. That just return the dq.front.first. What was the issue with this? I just showed you in the notes like 5 minutes or 10 minutes back that the issue was sometimes you'll have, like, let's say your DQ looks like this. 2, 7, 3. Okay. And your L is 2, R is, I don't know, 4. Okay. Then if you're returning the front, then that's incorrect because you'll return actually 10. But 10 is actually the first element of the array. Your array looks something like this: 10, 8, 7. Let's say the next element is, I don't know, 4. So you have a 4, 4. Okay, let's make it 5. So you have 5, 4. Okay, your DQ looks like this. Your L is 2, R is 4. Let's say the query function gets L as 2 and R as 4. And now you'll actually return 10, which is wrong in your trivial idea, in the trivial idea that we had earlier. What we want to do is we want to pop out 10, right? So we say till the time the DQ is not empty, if DQ.front.second, that is this index, this thing, the one, that is what index does this thing has. If this is less than L, that means the front of the queue is behind the range L to R. Then what do? We pop the front. So in this case, this thing after this iteration, like after this pop, will become this. And otherwise, we say we break. So the break is important because if you don't do the break, you'll just, like, you'll be stuck in an infinite loop. Like, even though this condition might not be true, like in the next iteration, this is 2 and our L is also 2. So this condition won't be true because 2 is less than 2 is false. So this condition won't be true. But if you don't have the else break, then you'll just be stuck in an infinite loop. So you need the break. After the break, what DQ do we have at the end? We have this DQ, right? And we just want to now return DQ.front.first. That is, now we are returning the front element of the DQ, which is 8. Okay, notice you can't call query in arbitrary order. Like, let's say, like I'm calling the query function in a very systematic order. I'm calling query 1k, then I'm calling query 2k plus 1, and so on. If I had done something like calling query 1k, then calling query 3k plus 2, then calling query 2k plus 1, this won't work. Your R should always be increasing and your L should always be increasing. Here, the R is increasing from this step to this step. So up till this point, it's okay. Up till this point, it's still valid. Like doing something of this sort, like calling query 1k and then 3 comma k plus 2 is still valid. But then calling query 2 comma k plus 1 breaks your L plus R condition, like L and R condition, because now you decreased L from 3 to 2 and you decreased R from k plus 2 to k plus 1, which is not allowed. So when we're popping out elements, it might happen that when we were doing L equal 3, R equal k plus 2, we actually popped out, let's say we actually popped out, yeah, exactly, Shruti is correct. The answer might be popped out because we might have popped out the value at second element. Let's say the value at second element was 8, right? And we would have returned the correct thing, which would have been 7. So we would have returned the correct thing. But the issue would be in the next iteration, when we come in and we see L equal to R equal k plus 1, our array would now only have this thing. Our array would be looking like this. So it won't actually have the second element, whereas second element was the largest amongst 2 to k plus 1 because it was 8. So we might have actually popped out the answer. So the L's and R should always be increasing in nature. And the sliding algorithm, only then the popping out method, like the popping out thing, doesn't affect your accuracy. So just like keep this in mind that you can't query any arbitrary range you want. You can't be like, I'll query now from 5 to 10, and then in the next iteration, I'll query from 2 to 7, something of that sort. You can't do that. Yep. So let's clean this code slightly. So the code is actually pretty small, like once you remove all the comments, obviously. And notice the like this structure of coding that you do something till the time the thing doesn't go empty. This is very common in BFS and Dijkstra, in a lot of things, that you do something till the time it doesn't go empty. In Dijkstra's also, you have a lot of Dijkstra code have this queue do while the thing is not empty, which basically means do while the thing while empty gives false. This is equivalent to this. Just the not using the exclamation mark is concise. Like it's shorter code, and yeah. So you can see in Vim I can delete multiple chunks of line pretty fast. That's like one of the benefits that I was telling you last time about. Okay. Yeah. And so let me look up what array we had in our mind. Yep. So we have this array, 5 elements, 3 as k. Okay. And then we have 5, 7, 3, 4, 2. Yep. So it prints out the first 3 elements max is 7. The next 3 elements max is 7 again. And the next 3 elements max is 4. So it actually did pop out these 7 correctly. Because otherwise, like the buggy codes for DQ sliding window generally, what they like the issue that they have is that when you're doing the thing for 3, 4, 2, you might still have 7 in your DQ. And so the last thing printed might still be 7, which shouldn't be. So anyone has any doubts regarding this code or like any of the functions? I mean, it's slightly complicated. Sorry for asking again, as I didn't hear your answer properly. Can we construct the entire DQ first and then calculate? Can you please explain how did you write the query function? Okay. So can we construct the entire DQ first and then calculate? Okay. So a case, no, you cannot construct the entire DQ first and then calculate. The main issue with that is that we are popping out stuff. So here we have this pop statement, which pretty much destroys what you're trying to do. Like it doesn't allow us to do what you are asking, that we construct the entire thing first and then do this. So what we want in our DQ at each step is that the DQ should contain only elements of the range L to R. We want this thing to be preserved, that at any moment of time, DQ should only contain the elements from L to R. So when we are pushing an element, let's say currently L is 1, R is K, right? After this point here, L is 1, R is K. At this point, we have only inserted the first K element. Now in the next iteration, we'll push R at K plus 1. So we'll call the push function here, line 49. And then in the query function, we'll actually pop out L as 1. Like L as 1 will be discarded. And L will actually become 2. So this statement is not strictly true. DQ should only contain elements from L to R. It can contain some smaller elements also. It can contain L minus 5 or something. But you know for sure that the head of the queue, that is the front of the queue, should be between L to R. If it's not, we'll pop it out here, as you can see in the query function. Okay, so people are asking me, why is the thing order n? Yeah. So the thing is order n because, okay, think from this perspective. Although you have while loops, so it becomes complicated. Like, how are we doing the analysis? Because we have while loops. Think from this angle. How many times is an element inserted into a DQ, into the DQ? So how many times is, let's say, the third element inserted in the DQ? Once, right? In the push function, it's only inserted once, right? Here at line 18, DQ.pushback. It's never inserted again in the DQ. And how many times is the third element popped out of the DQ? That is removed from the DQ. Like popped out just means removed. Popped out / removed from the DQ. Once, right? Like it can happen that the third element got removed here, like at line 13, or it might happen that it got removed here at line 27, like somewhere in the query function or in the push function. But we know that once it's popped out, it's never inserted back again, right? So at most, the amount of cost the third element costs you is 2. Like it's inserted once and it's popped out once. So it costs you order 2. And how many elements do we have? We have n elements. So it costs you order 2n. If you want to think about it in a more precise way, do something like this. Have a global variable or cost. Okay. And whenever you're doing a popback, do a cost plus plus. Whenever you're doing a pushback, do a cost plus plus. Whenever you're doing a pop front, do a cost plus plus. Okay. Now I am claiming, I have a conjecture that cost will be less than equal to n. Cost will never be more than 2n. So that's why the complexity is basically order n. Because cost is like whenever I'm incrementing the cost, I'm actually trying to denote a iteration or a step in our algorithm. Here we had a cost plus plus because this while loop ran once. Whenever the while loop runs, this cost plus plus gets incremented. And when it gets broken, obviously we don't want to increment the cost anymore. Here also I'm incrementing the cost because there's a pushback. Here also I'm incrementing the cost because there is a while loop and we are like constantly popping out elements. So you can just think that how many times will the cost be incremented? And it's 2n. And the reason why it's 2n is because of this thing, that how many times is a particular element, here I'm picking 3, but how many times is a particular element inserted into the DQ, that is once, and how many times is it popped out, that is also once. So for a given element, it costs you order 2. Like third element costs us 2 operations. So n elements will cost us 2n operations. Right? Yeah. So any doubts regarding the complexity? The complexity is order n because of the cost thing. Like the way the cost moves. In sliding window algorithms, generally always the complexity comes out to be order n, although it might not look like the complexity is order n. Yeah. And someone was asking, well, how does the query function work? So we had the trivial idea, right? Everyone is clear with the trivial idea that why we were trying to do dq.front.first, because we were maintaining the invariant, which was dq is descending. So if we print cost, it will be 2n. It will be more like less than equal to n. Like I'll print the cost here. So like I can ensure you that it will be less than equal to 2 times. It might not be 2n at the worst. It will be 2n at the worst case. It might be smaller than. Yeah. So see, the cost came out to be 8. I didn't put an end line after this, but like 8 is the cost, and yeah, 8 is less than 2 times 5. Yeah. So yeah, I'll just go through the query function again. So the invariant was that the DQ is descending. So the trivial idea or the old idea, which is slightly incorrect, was to just return DQ.front. This is happening every time if condition will be not true. So if we print call, I don't get the doubt exactly the ones. This is happening every time if condition will not be true. Which if condition are you talking about? This one? I don't know. I mean, there are a lot of if conditions. Can you talking about cost? Okay. So I'm saying that cost is trying to account how many steps does the algorithm take. Like that's what we want to do, the cost variable to denote. Like cost is less than 2. Yeah. We want the cost to denote how many steps does the algorithm take. So we are incrementing it whenever we are doing an operation. Okay, if you want, you could have done a cost here also, plus here also if you want. But then you'll just get the bound. Let's say I do it in the else's also. Then my bound will be 3n. At least that's what I think it will be. Yeah, I don't think I'm incorrect. Then it'll just be 3n. That cost is less than equal 3n. It won't be 2n anymore. But it's still order n. It doesn't matter. Like I'm just using the cost variable. I'm just trying to show that the algorithm itself is very fast. It's not taking nk steps or n square steps. Like even if k was n by 2, the trivial order nk algorithm would have taken n square steps. But by cost, I can show that it's 3n, which means our algorithm is taking order n steps. Okay. Yeah. So I think that's pretty much all the question. I mean, if still people are doubtful about the query, then I can go through it again. But yeah, otherwise I can just like end this question here. You guys will like in the chat section if like the query is still not clear. Yes, Tiwari has raised hand. I mean, you can just ask the question. Thanks, you okay, Shubham understood. Anyone else like having doubts? Like, okay, I can probably. Okay, good question. Good question. So someone is asking, can we modify this slightly to find the maximum? Like, if there is 45426 and k is 1, 2, the answer is 46. No, maximum sum sliding number. So you're saying okay, I don't get what Vishnu is exactly asking. Okay, but like the way I understand his question is that he's basically asking, what if we wanted to find range sum? Like let's say the array is, let me give back 5, 7, 3, 4, 2, k is 3. Then our answer will look like this. So initial thing will be 5 plus 7 plus 3. Then it will be 7 plus 3 plus 4. Then it will be 3 plus 4 plus 2, which is 15. Then 14. Then 9. Let's say our question was this: how to calculate subarray sum for every subarray. Then you actually don't need DQ. I mean, DQ is a very complex method to do that. Like, then like you'll probably get a simpler approach using something like this. Like, I don't know, end answer equal 0. So I'll just comment this out. Answer plus equal AI. Then we print out answer. I mean, this code then generally works, right? That is, for which question are we talking about? What are we talking about? Okay, so right now we are discussing theory, right, Devansh? And the question that someone asked, Vishnu was asking, was that, okay, Vishnu, you can actually message everything in the group chat. So I'll just copy paste the question that he was asking. Yep, he was asking something like this. I don't get the exact example here, but what he was asking was that how to calculate the subarray sum for every subarray of size k. That is basically, instead of subarray max, we have sum. So this is actually a much simpler question. Like, I think a lot of people would have seen this before, which is basically do something of like you have an answer variable which basically first considers the sum of all the first k elements, and then whenever you add a new element, you insert it and you remove the contribution of the element from behind. So I'm removing the contribution of the element I minus k. You get it? Like, I'm first adding in the r plus 1th element, I'm adding in the k plus 1th element, and I'm removing the first element. Then in the next iteration, I'm adding in the k plus 2th element, and I'm removing the second element, and so on. So I just have a single variable and that thing does the work. In max, you can't do this because you can't have like answer equal max of answer comma AI. You can do this, but how will you remove the AI minus k value? Like, how will you say, I don't want this value inside me? There is no easy way to say that. Yeah, the DQ logic won't extend. And it's an overkill also, to be honest. Like, you might be able to extend it, but you wouldn't want to go through such a painful path for the problem, like, because it's a very simple problem in the first place. Okay. Another thing. So for this question, I'll leave two homeworks. Homework one will be, I'll put them on the discuss also after the update. There has an update. Homework one will be to try to solve the subarray max problem using sets or maps in order n log n. So n log n is still better than order nk. It's still much better than order nk. And the benefit is that like n log n is still pretty fast. So even if you can't get the DQ logic entirely, sometimes you can still get n log n, which works a lot of times. And homework two is try to solve the same problem in ON using prefix suffix max arrays plus partitioning idea. So this is more like an idea. I'm not going through this idea right now. I'll put this up. And Mole is asking, can we use priority queue for the same inserting window size? Okay. Yes, you can use a priority queue. Yeah. Although do not, in priority queue, like we'll cover this in week 3. I think probably someone will cover it in our live session of week 3. That inserting things in priority queue is simple. You can just do PQ dot. I think you can do PQ dot push, right? Yeah. And put the thing there. But there is no PQ dot erase a particular element. You can't erase a particular element in a priority queue. You don't have this functionality. You have that functionality in sets. You don't have that functionality in priority queue. So the interesting thing is, how do you erase stuff from PQ? But you can do that. So it's a good practice. Like if you want to do it using sets or maps or priority queue and login, then you can try it. And homework 2 is actually slightly hard. I'll probably share a link with you guys, which shows an alternate to DQ for the same problem meant to be done in when. So it's as fast as this approach that we currently discussed. And I mean, the benefit is that that approach is slightly simpler, but it's very hard to get the idea of that. Okay, there was saying that in Java there is. Okay, might be, but like I know for at least like for C++, you can't insert you can't delete a particular element from a priority queue. You can only delete the topmost element. That is the smallest element. So Aryan is asking, how would that even work? I mean, yeah, if the priority queue is actually implemented like a heap internally, then I don't think that pop will work. But like, let's skip that portion for now, because I think a lot of people aren't familiar with priority queues right now, because it's still content of week 3, and like I guess people would still be reading through those things. So this was dq.cpp. Like final question for any doubts, or like you can just take these 2 homework questions with you. Yeah. And like I'll probably share this entire DQ code also on the discuss chat after this stream ends. But yeah. All right. Looks like we don't have any questions. So yeah, I think the stream is running since like 1 hour. Can you share this code? Sure. And I would recommend we take a break for like 5 minutes. Like you can go through the DQ code, and after the 5-minute break, we can cover Z rectangles question at least first. So we have this question, ZCO 1504, right? And here's a brief description. So you have a 2D plane, 10,000 units along the x-axis and only 500 units along the y-axis. That is, your x-axis goes from 0 to 100,000, sorry, and y goes from 0 to 500. Origin is 0, 0. And he's just defining the corners. That's, we don't really care about this. We're also given the coordinates, a set of endpoints inside this region. The points have only integer coordinates. Okay, an important thing is they do not appear on the along the x or the y axis. So they don't have edge cases like those, the tricky edge cases. So the point basically given is that no point can have like 0, something or something, 0. There can no point be like 0, 10 or 10, 0, whatever. So we want to draw a rectangle with its base on the x-axis of maximum area, right? Such that all the endpoints, like such that none of the endpoints lie in your rectangle, like lie inside it. The points can appear on the boundary, but they cannot lie inside. So it can appear like one of the edges of the rectangle is coinciding with the point, but the point shouldn't be completely inside the rectangle. So here they've gone through an example and blah, blah, blah. The area that they came out to was this. We don't care about this stuff much right now. And these are the two constraints. So you can notice that here probably n square will work, right? That is, if you have n points, something of the sort n square algorithm will work. But here you probably need something like order n or order n log n or something fast for the entire thing. And that's pretty much the question, right? So one thing that like I or most like all the people do is that they first try to like, even before coming to logic, sometimes people do this, that what do we need in the implementation? So the maximum answer possible here is this thing multiplied by this thing, right? 100,000 multiplied by 500. So this is how much? This is 10 to the power 5. And this is 5 into 10 to the power 2. So the product will be 5 into 10 to the 7. And we know that an integer can store up till 10 to the 9, or more precisely 2 into 10 to the 9. So our answer will never exceed integer. So don't use long log. That's it. Like a lot of people, whenever they see such huge numbers, they automatically go for long longs. But I mean, it's a good practice for beginners, I would say. Like initially, if you're doing that, always opt for long longs. But later on, you'll realize that that's like, it's unnecessary because it sometimes make your codes like 2 times slower or 3 times slower. And like sometimes that's the difference between getting a accepted or a TLE, that your code is barely passing or not passing. So long longs generally make your code slow because they're bigger. So any arithmetic on them is also like twice slower or like at least slower than integers. Right. So like right off the bat, we know that our answer can be stored in integer because the maximum answer can be 10 to the power 5 times 500, which is 5 into 10 to the 7, which is less than 1 second. And like the time limit here is 1 second. Okay. Devansh is asking, so long can get me daily. Not for this particular question, Devansh. I don't think long will actually bother for this question. Like it'll actually make a difference. But it's a general practice that you should try to inculcate, that don't use long if you don't need it. Like just try to calculate the worst case of the problem. Like what's the maximum value that will ever come in the question. In this case, we know that the answer can never be bigger than this thing times this thing, right? 110 to the power 5 times 500. It can't be bigger than this. So we don't need long longs. It might have happened that we needed long longs, like this thing was actually bigger. Then we should have used, obviously. But don't use them unnecessarily, because otherwise in some problems you might be stuck in the TLE scenario. Obviously in this problem, I don't think you'll be stuck in the TLE scenario, because if your solution is order n, then even if it's a slow order n, it will still pass for 10 to the 5. If it was 10 to the 6, it might have been the case that it's actually slow with long longs. All right. So this is the question. Now I'll switch my screen to the whiteboard because, yeah, like I think like this is like a hard question, I would say, as in because it's the most unsolved and but it's quite popular also at the same time. Sharing is paused, blah blah blah. Okay. So I'm hoping everyone can see the whiteboard, right? And yep, here we have, okay. So our test case, okay. So in our test case, what all points do we have? We have 1,4, we have 2,3, we have 3,2, we have 5,1, and we have 5,2. Let's work out the sample first. Right now, this is our x-axis, this is our y-axis. Let's try to plot all those points. So 1, 2, 3, 4, 5, and dot dot dot. Here also 1, 2, 3, 4, 5, and dot dot dot. Okay. Now the first point is at x1, 4. So here. The next point is at x2, y3. So here. The next is at x3, y2. So here. The next is at x5, y1. So here. The next is at x5, y2. So here. All right. These are all the points. Now, so what are valid rectangles here? Those rectangles that touch the base. So example. Okay. Also, the rectangle's endpoints must be integers. So it can't end at like 2.5. It can't end at like, yeah, non-integer positions. So one possible rectangle could be, say, this thing. This is a possible rectangle. Another could be, say, this thing. This is a possible rectangle. Okay. Another could be, say, this thing going on till 10 to the 5. Like I'm just showing multiple possible rectangles. And the question is basically asking which is the maximum one, which has the one that has the largest area. Okay, Swagat has asked a very generic question. And like, honestly, I don't know how to answer this, how to become 5-star. I mean, I don't know, honestly, like probably cover all the topics in this series and yeah, practice a lot or no, maybe not a lot, but a bit. And yeah, not only on CodeChef, maybe on CodeForces or other platforms also. But anyways, let's move forward. So, so this is a question, right? Yeah. And we have to find the maximum rectangle. Like by maximum, I mean the rectangle with the highest area, the maximum area. We don't even have to find the rectangle itself. We just have to find the area. Okay. So observation 1 would be, like the first observation that should be there is that a maximum rectangle, like if a rectangle doesn't touch any of the points, then it's a useless rectangle. Let me restate this again clearly. If a rectangle doesn't touch any of the points, then it's a useless rectangle. What I mean is, let's say there is a rectangle this. Let's say we make this rectangle. It's a pretty useless rectangle because we can expand it. If it's not touching the points on any of the side, then we can expand it, right? We can expand it in this direction, we can expand it in this direction. So it's a useless rectangle. Like it will definitely not be the largest one because it's not touching any of the endpoints. If it's not touching any of the points, that means it can be expanded. And because it can be expanded, it's definitely not the answer because there is another rectangle which is bigger than it, right? So this is definitely a useless rectangle. Okay. Although this might not be a useless rectangle, right? This is not a useless rectangle because it's touching. So like it's a possible candidate, right? Okay. Let's come up with a more precise definition of this thing. So I'm removing the sample right now. Let's create our own points structure. So let's say 1 has, let's say, a point here, 2 has a point, 3 has a point, let's say here, 4 has a point here, 6 has a point here, okay, 2 has a point here, fine. And 0, we can assume that there is a point at infinity on 0, that is at 500, and there is a point at 500, so that we don't go outside these bounds. Okay. Now, the idea is that, okay, observation 1 was that a rectangle is useless if it doesn't touch any of the endpoints. Can this problem be viewed as some kind of optimization problem like LPP with constraints as line segment choice points? And the way you're discussing is that what we call a constructive algo. Rakesh, not really. I mean, okay, I still haven't come to the approach right now. And okay, you can think of this problem as a LPP, although it's like a slightly overkill and it's a very mathematical view of the problem. But if you think of the problem as LPP or something, the issue would be that you won't be able to exploit the two-dimensional properties of the problem. That the problem is in two-dimensional and the property that the rectangle always has to touch the base. I don't think it will be very obvious in the LPP that you're trying to exploit those facts. And this question actually boils down to stacks eventually. Like stacks are basically solving a subproblem. Okay, Shruti is asking what's LPP. So LPP is basically linear programming. It's basically, I don't know, in math, 11th grade or 12th grade, you have like basic idea of like simplex or something. And that's where the topic comes from. It's a math topic. And yeah, I don't know how to explain it more. I mean, you don't really need that in comparative in general, like knowing how to solve LPPs or something. But yeah. So for this question first, so our observation 1 was very crude. It was saying that, so let's redefine observation 1. Now it will be something like this. So I'll write it out clearly. If a rectangle doesn't touch a point on its top side, then it is useless. Okay, doesn't touch a point on its top side, left side, and right side, then it is useless. Okay, now this is our observation. What it means is that this rectangle is also now considered useless by us because it's not touching any point on the left side or the right side. Like this entire segment doesn't consist of any points. So you might have as well expanded it. Like this thing could have gone till here, right? And this thing could have gone till here. You won't call this rectangle as useless now. Like this rectangle is not useless anymore because it's bounded by points on the left side, right side, and like all the sides. Okay. Although on this side, it's not bounded by any point, but it's bounded by the like the 0th line, which is like our default. We can't go beyond this. That's like common sense. Right? So, okay. So think about all those rectangles. Think about all those useful rectangles that end at height y, that end at height h, sorry, h. Okay, so let's say there is a rectangle whose height is h equals 2. So what all rectangles can you think of? What all useful rectangles can you think of that end at h equal to? Anyone? What all useful rectangles can you think of whose topmost point ends at height equal to? Okay, I don't get any message in the chat, so let me explain this. 0, 2 to 10,000, 2. Yeah, I think it's correct. So it's basically this thing, right? Going till indefinitely till here. Like this is actually 10,000 to 100,000, whatever. So this rectangle is valid, but no other useful rectangle you have which ends at height 2. No other useful rectangle. Similarly, which rectangle do you have which ends at height 3? Useful rectangle which ends at height 3. There will be multiple rectangles. I'm just asking you to give me an example. I can give you one example here. One example would be this rectangle. Okay, that is 0, 3 to this thing, which is basically 6, something. X is 6. I mean, I don't know how you're counting coordinates. So it's 0, 0 to 6, 3. Yeah, I mean it's correct. So this is also useful rectangle, right? the idea that I'm trying to like inculcate here is that your useful rectangle is always bounded by a top set, right? And at height equal 3, it was bounded by this guy. This was the important guy. Like this was the guy that was restricting our flow. You couldn't go above him, right? So basically, every useful rectangle has a top guy who's bottlenecking him. For this rectangle, our top guy was this guy who was bottlenecking the entire rectangle. For say, I don't know, let's say this rectangle. So this is also a useful rectangle by our definition, right? For this rectangle, our top guy is this guy because he's bottlenecking the top side. So this is the bottleneck. That is, we can't go above this thing for this rectangle at least, right? So the idea is that given, like, if you fix a bottleneck, let's say you fix the bottleneck, let's say you say that, okay, I'm trying to count the best rectangle with the bottleneck, which is this. I'm trying to calculate the maximum area rectangle whose bottleneck is this guy. Then what I mean is that your y line will be like this of the rectangle. Now you have to find the x point, right? So your left endpoint will be somewhere here. Your right endpoint will be somewhere here, right? Your left endpoint will be somewhere to the left of 3, and your right endpoint will be somewhere greater than 3. Now, can your right endpoint be here? No, because this point comes inside, right? So your right endpoint can be here, 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 or here, right? And it will obviously, because we are finding only useful rectangles, it will be at this guy, right? What property does this guy have? So 6, 2 is the first guy who's lower than this guy, 3, 3. So if you think about all these points in a vector, like this point, let's say label these points, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6. Let's label these points. And if you think about them, all of them present in a vector, then what are they? Let's think about the coordinates in the vector. We'll have 1, 4, then we'll have 2, 4, then we'll have 3, 3, then we'll have 4, 4, 5, 4, and finally 6, 2, right? If this is the vector and this is our bottleneck, how much to the right can we go? We can go to the right up till the point we find a coordinate whose y is smaller than ours. So our y is 3. If we find a guy whose y is smaller than us, then we stop. So we stop here. Let's say there was another point here. Let's say there was a 7 and that guy was like here, which was 7, 5. Okay. Then our thing would look like this. Here it would look like 3, 3, then 4, 4, then 5, 4, then 6, 2, then 7, 5. Now, if our bottleneck is 3, 3, the number of steps we can go to the right before we hit our right endpoint, right extreme, is still this thing, because we compare this y coordinate and see which is the first guy to our right whose y is smaller than ours. So this guy's y is 4. 4 is greater than 3, greater or equal 3, so we skip it. The next guy's y is 4, so we skip it. The next guy's y is 2. 2 is not greater or equal 3. That's not true. So we stop here. Similarly, we go to the left and we stop here because we have a 0, 0 dummy entry. Like 0, 0 will be inserted as a dummy entry because we don't want the guy to go beyond, like to the left of 0, 0. Everyone gets this? Like once we fix the bottleneck, how much to the right can we go of the bottleneck can be found by saying in the vector of sorted x's of all the points, which is the guy immediately to my right who has a lower y coordinate than me. I'll like say the statement again because it's a pretty long statement. So once we've fixed the bottleneck, we want to find a right point, that how much to the right can we go? And to find that, we say in the sorted vector of all the guys and sorting the points by x's. So we have sorted the points by x's, x equal 1, x equal 2, so on. We've sorted them by this. Who is the guy that is immediately right to me, whose y is smaller than me. So for this guy, which element is the element that is immediately right to 3,3, immediately right of 3,3, and whose y coordinate is smaller than 3? That is 6,2, because it's the first element whose y coordinate is actually smaller than 3. So we know that our bottleneck will be here. Like, yeah, had this point been here, then our bottleneck would be here. Does everyone get this? It's slightly complicated, but like, I think that's the easiest way to say it. That what's the point to our immediate right that has a smaller y than us? That guy will actually be the limit to up till which we can extend at this height. Are we fixing the top bottleneck? Yes, we are fixing the top bottleneck right now. So we are saying that our rectangle's height will definitely be 3 because we are fixing the bottleneck. Like, we are fixing the height, and we are just trying to stretch it to either to the left or to the right. So when you think about why a y coordinate should be less than height's y coordinate, okay, good question. So yeah, I mean, let's say the y coordinate of 6 was actually pretty big, right? Like, let's say the y coordinate of 6 was actually 6,5, and then there was an 8 which was actually 8,3. Now think about 8,2. Okay, somewhere here. Okay, now think about this. Will you, like, when you fix the height at this thing, will you stop at sixth position? No, you can still go on, right? You'll still go on. You won't stop here. You'll still go on. But you'll stop here, because if you go after this point, like, you can't include this point inside. So you'll have to stop at 8th position. So by stopping at 8th position, what did you say? You basically said, okay, I found an element at 8th position whose y is smaller than me. And because this guy's y is smaller than me, I can't extend beyond him at this height, at height equal 3. Like, I'll have to drop my height if I want to expand beyond him, which I don't want to do because I've fixed my height already. I've said that my height will be 3 no matter what, because my bottleneck is 3,3. So you're like, the height of the rectangle that we're considering is the height of the rectangle whose bottleneck is 3,3. How do you fix 3,3 as top bottleneck? Why not some other point? Yes, Vishnu, that's a good question. So this was just an example that I was showing, that we fix as 3,3. Actually, in the entire algorithm, we'll try to fix every point as the bottleneck. Okay, so if there's a coordinate at 9,1, yeah, let's say there's a coordinate at 9,1, you still don't care, because you can't, when you come at 8, you see that there is a point whose y is smaller than me, so I should stop here, and you'll just stop here. So, okay, whatever I'm saying right now only considers the fact that our bottleneck is 3,3 right now. But Vishnu was correct in asking that why is 3,3 magically pegged? It's not magically pegged. We'll actually try for every single point, keeping it as bottleneck. Okay, Devansh is asking why can't we stop at 9,1? Okay, the reason why can't we stop at 9,1 is because, let's say we stop at 9,1. What happens? The issue is that 8,2 came inside a rectangle, right? 8,2 is now part of the rectangle, which is not allowed. Area will be larger, you're correct, but 8,2 shouldn't have been part of the rectangle. So that's why we stopped before. That's why we stopped at this point, because we don't want 8,2 to be part of the rectangle. So the first point that's smaller, that's where we should stop, because if we expand beyond this point, we'll definitely include 8,2. Okay, what if no such coordinates are present to satisfy the condition? Yes, good question. Yeah, people are asking good questions. Okay, if there is no such point, then your terminal case, or basically your base case of some sort, will be to keep on expanding it till the time you hit 100,000. That is the limit. Yes, exactly. What are you missing? Then the dummy point will act. And in our case, we can have a dummy point at, say, 100,000, 0. Like, just create a new dummy point at 100,000, 0. And like, although that point doesn't exist in reality, we'll just create it for our simplicity. So we'll create a point 10 to the power 5, 0. So what will happen is, at this point, we'll say, okay, our rectangle must stop here, because you can't exceed this, because if you exceed this, you'll include this point. So you'll automatically stop here. So inserting the dummy points is a very clever way of handling the edge cases. which a lot of people do a lot of times, that instead of trying to code an ugly if else condition, you try to think of how I can put in more things inside the thing so that the edge cases work out themselves magically. So this is an edge case which you're asking. So, okay, coming back to Vishnu's other question, which was, we are not actually picking 3,3 as the only guy. So let's say there was an 8,2, right? In a future iteration, we'll also pick 8,2 as the bottleneck. We will. And then what we'll do is from 8,2, we'll try to extend the left window, and we won't find anything. So we'll keep on extending it till here, and we'll try to extend the right window. Let's say there was a point 9,1, which the person suggested. Then our right window will only be extended till 9,1. So we'll even consider this big rectangle. So it might happen that this big rectangle, like let's label this rectangle. Let's say this is rectangle A. It might happen that rectangle A is actually bigger than the area of rectangle B. Rectangle B was the rectangle which was bottlenecked by 3,3, which ended at x equal 8, and on the left side ended at x equal 0. I haven't calculated the areas exactly, but it might happen that this rectangle A was bigger than rectangle B. So we are actually considering every rectangle like this. Like we fix a bottleneck and then we try to find the maximum rectangle at that bottleneck. Is everyone clear with the idea of the problem? Like what's the n square method? Don't go for the order n method right now. The n square method is basically a lot of ugly. Can there be a left boundary for a bottleneck? Yes, okay. So Shaunak asked, can there be left boundary? So what I just showed right now was the right boundary, but you do the similar thing for the left boundary. So let's say I'm creating another example because I think this one is like, you guys got too familiar with it. So let's say the one and the two, then 2 guys is like pretty big, 3 is pretty big, 4 is pretty big, 5 is pretty big, 6 is pretty big, right? And 8 is here. Yeah. And let's say our bottleneck is this guy. Now, when our bottleneck is this guy, we have already fixed our height to this thing. Let's say the height is 5. Okay, we have already fixed our height. So now we want to stretch from here to the left and to the right. How much can we stretch to the right first? We can stretch till this point, right? After this point will definitely be included, so we can't go beyond this. And similarly to the left, we can stretch till this point, because after this, again, this point will be included. So we try to stretch on both sides to how much left can we stretch and how much right can we stretch. I think after 3,3, our next point should only be such points which are above 3,3, as it would reduce our test cases. I don't get what Dhananjay is exactly saying, but I mean, you're right. Oh, okay. Shruti is asking, can we do it in some other way, fixing a left or right bottom? Shruti, I don't think so. Yeah. I mean, because the question has a symmetry of saying that your rectangle should always touch the x-axis. The question doesn't say that your rectangle should always touch the y-axis. That's why we are fixing the bottleneck on top. I mean, I don't have a simple answer for this, that why can't we fix the left bottleneck or the right bottleneck, but I know that doesn't work. So we do Sargo for each point, yes. Like right now I'm doing it for this point and I found the maximum rectangle. Let's say this is the rectangle. Let's say the area of this rectangle is 30. Then I do this for this point. So the rectangle comes out to be this thing and this thing. Let's say the area of this thing is 28. So we compare and we pick the best guy, like whose rectangle gave me the max. Yeah, and we found the max. And the important thing here was that when we're considering only these rectangles, we won't miss out on the optimal rectangle. Let's imagine that there was some best rectangle present in the solution, right? In this test case. Notice that this strategy won't miss out on that rectangle, because the best rectangle must definitely be a useful rectangle, useful by our definition, that it should definitely be bounded on the top side, on the left side, and on the right side. Plane and not a point. Okay, yeah, Aryan has another interesting question. So it might be the case that you're given, like, let's say at the fourth coordinate, at x equal 4, there is actually no point. but it still might be the case. You'll still have to consider this rectangle. And this rectangle actually ends at 500, like height equal 500. That's the topmost height. What Aryan is saying. That, yeah, I missed this case, but yeah, that like even this is a useful rectangle because it's still bounded at the top side. Although there is no point at the top side, but there is still an edge on the top side that we can't exceed. We can't go till 501. And on the left side, on the right side, it's bounded by these 2 points. So we even have to consider rectangles like these. In considering rectangles like these is easy. You can just consider, you can add more dummy points. You can add points at 0, 500, 1, 500, 2, 500, so on. So there will be a point at 4, 500. And you'll consider that also, right? That's easy. So like adding dummy points simplifies your edge cases a lot. And I'm not adding a lot of dummy points. Notice that also. Like when I'm adding these dummy points, how many dummy points am I adding? I'm adding 10 to the 5 dummy points. And when I'm adding a dummy point here and dummy point here at the 2 extremes, I'm adding 2 more dummy points. So I'm only adding order n dummy points, which is small because originally I have n points. Now I have added n more points. So I have 2 n points. If our algorithm is going to be order n square, now it's 4 n square at most. So it's still okay. It's still a 4 constant factor thing. So adding n dummy points doesn't actually make your solution much slow. Obviously, we don't want an n square solution. We actually want an order n solution. So after adding the dummy points, it will actually be order 2n solution, but we don't care. Like 2 gets dropped from the complexity. Right? So everyone got that we want to fix bottlenecks, and then for a bottleneck, we want to expand to the left and to the right. And once we've expanded, like that rectangle is considered. Won't just 0, 500 suffice instead of 25 points at the top? No, 0, 500 doesn't suffice because think about this. If you have 0, 500, but you don't have 4, 500, will you ever consider this rectangle? You won't consider this rectangle because when you consider 0, 500, you'll actually end up considering this rectangle. Right? Like you'll fix the 0, 500 as the bottleneck. Then you'll say how much to the left can expand and it will be this much. And how much to the right can expand, it will be this much. That's it. You can't expand further than this. So you won't actually consider this rectangle as a case. To consider this rectangle as a case, you need to input this point. Or maybe this point or that point. Like either of these 3 points. How to determine the left bottleneck? Okay. The left side bottleneck, yeah. So the left side extreme and the right side extremes, like first we'll go through the naive way of finding the left extreme point and the right extreme point. That's top our answer, which will be n square. And then we'll try to show how stacks can be used to improve that thing. Okay, but that's a later part. Like using stacks for that thing is the later part. So, okay. So I'll erase a lot of stuff here. I'll erase this observation. I hope you guys can remember this observation that we only care about those rectangles which are bounded on all the 3 sides. Since the question doesn't say include maximum number of given points in your rectangle, why not take the rightmost point as start and go till the last dummy point always? Okay, Vishnu, that doesn't work because here I'm considering very small coordinates. Let's say your rightmost guy was at 99999 and he was here. So his coordinate was 99999 Now, when he'll go to the dummy point, he'll just cover 1 unit square. Right? The issue with your method is that it's not necessary that the x's end up being very small. It might be that the x's are actually spread out evenly till 10 to the power 5. If that's the case, then your strategy doesn't work. That pick the last guy and then extend from that. Right? Like if this was a point, then the last rectangle would just be this much. So yeah, but nice question. Yeah, sometimes problems do have simple solutions. So yeah, you should think about easier solutions. Let's see. So yep, so let's say this is our point, and let's say the window made is this much, right? So I'm going to erase this observation and then try to show you guys how does this algorithm work in N-square. Okay. So firstly, consider all the points in sorted order present inside a vector. In sorted order, by sorted order, I mean sorted by x's, right? So when they're sorted by x's, it's like 1 comma 2, then you have 2 comma something big, let's say 8, then you have 3 comma something big, let's say 7, then you have 4 comma 4, then you have 5 comma I don't know 7 again, and then 7 comma let's say 7, right? And now let's say we fix the bottleneck as 4 comma 4, this guy. Then we'll say to find the right bound, we just need to find, okay, let's say this is 8 and this is 3, so there is 8 comma 3 also. To find the right bound, we'll say just go and find the first point on the right whose y is smaller than ours, so it's this guy. And to find the left bound, we'll say just keep on going to the left and find the guy whose y is smaller than ours, so it will be 1 comma 2. So here, okay, it might be the case that there are more elements after 8 comma 3, but we don't go there because we stop here, because the condition is that the y should have dropped below ours, which is 4. So it dropped below 4, so we stop here only. So this is our right bound, this is our left bound, and this is our bottleneck, right? And once we have these 3 things, we can calculate the area. The height is 4, the left bound is 1, the right bound is 8. So the area will be r minus l plus 1 times h, which is 8 minus 1 plus 1. Sorry, the plus 1 is not there. Yeah, just the r minus l. So 8 minus 1, 7 times 4, so 28. Why not smaller than or equal to? Okay, good question. But like, think about this. If this was actually 8 comma 4, if this point was actually at this position, 8 comma 4, then you could take it and still go on. You don't have an issue. Like if it was 8 comma 4 and there was a 9 comma something big, and then there was a 10, there was a bottleneck, like let's say 10 comma 2, like there was an issue, then you could go till here. You need not stop here. So it will be on the boundary, it will be on the top edge, but you don't need to stop here. So if it was 8 comma 4, you could actually go ahead and pick the guy whose thing is smaller than you. So the guy who's smaller than you, only that guy creates an issue. The guys that are equal to you, they don't create an issue. Right? And also, obviously, if there is a guy smaller than you present on the same x-axis, then also he creates an issue. He basically doesn't allow you to create any rectangles. Let's say there is 4 comma 4 and there is another guy at 4 comma 2. Then you can't create any rectangle, because no matter what you do, this guy will be included. How do we go about deciding bottleneck? So Kaveri asked this. We pick every point as a bottleneck. So in this case, I'll show you the order n square method. So we first fix our bottleneck as 1 comma 2. We fix everything as a bottleneck. Like we try out each guy as a bottleneck. So we first fix the bottleneck as 1 comma 2. Then we say, what is the left point? The left point will be 0 comma 0. And what is the right point? The right point will come out to be, let's say, I don't know, 10 comma 1. Let's say there is a 10 comma 1 here. So the left point will be 0 comma 0. The right point will be 10 comma 1. And this will be the bottleneck. Then we get our answer. Let's say the answer is A1 for this rectangle. Then we fix our bottleneck to 2 comma 8. We again try to calculate what's the left point, what's the right bound. So the left bound will be again 0 comma 0. The right bound will be 3 comma 7. Notice why it's 3 comma 7. Because when you go to the right, who's the first guy whose y is smaller than you? It's 3 comma 7, right? 3 comma 7's y is 7 and his guy's y is 8. So he's the first guy. So you stop here and you stop here. and you get the answer, which is A2, and you keep on doing this. So how many bottlenecks do you have that you're trying? You're trying order n bottlenecks. You're trying all the n elements, right? And how much time does it take to get the answer for that bottleneck? It takes you n steps, because once you fix the bottleneck, let's say you fix the bottleneck as 2,8, then you need to go plus to the right and see when does it break, when do you have an issue. So in this case, you're lucky that the issue came very early, it came at 3,7. But in the worst case, it might happen that the issue came very late. Similarly, you go to the left and again try to find an issue. So when you're going to the right, how many steps does this thing take? This thing takes at most order n steps, going to the right and finding the bottleneck. Similarly, going to the left and finding the bottleneck takes you order n steps. So in total, it takes you order 2n, which is again order n. And you do this for each bottleneck. So number of bottlenecks multiplied by cost it takes to calculate the best rectangle for each bottleneck, which is n squared. Right? Everyone gets stuck till this part, that how will an n square algorithm be coded for this problem? Can we traverse from right to left to check bottlenecks? Yes, you can. I mean, it doesn't matter. Like in the n square algorithm, at least, no matter which order you're picking bottlenecks in, it doesn't matter. But obviously, when we are using the stack technique, we want to get an order in. That time, it will matter how we are calculating the bottlenecks. Okay. So for now, just think with this n square algorithm. Like everyone should be clear with the n square algorithm, because the ordering algorithm is just going to be slightly like more complicated than this. So at least this much should be clear. Like if you have any doubts up till this point, just ask, because the next thing will be harder than this, and it will use this as a prerequisite. You'll need to understand how this one works before. Can you repeat once? Shonik, which part? I mean, I can't repeat the entire thing again because, yeah. N square. Okay, sure. So the number of bottlenecks that we had were n, right? Like we were trying each element as a bottleneck. We were trying 3,7 as a bottleneck. We were trying 4,4 as a bottleneck, and each guy. So the number of bottlenecks that we had were n. And for each bottleneck, it took us order n time to get the best rectangle for that bottleneck. So let's say our bottleneck is 4,4. Now, how much time will it take to find the right bound? It will take you at most n steps, less than equal n steps, to find the right bound. You'll keep on going plus and find the first guy whose y is smaller than you. So that's 8,3. And similarly, to find the left bound, you'll keep on going minus and find the first guy whose y is smaller than you. So that's 1,2. So that will take you at most n steps plus n steps, because going to the right can take you at most n steps, going to the left can take you at most n steps. So in total, it will take you at most 2 n steps, right? So given a fixed bottleneck, top bottleneck, how much time does it take you to get the best rectangle? That's order n, that's 2 n steps. And how many bottlenecks do we have? We have n such bottlenecks. So n bottlenecks, and each bottleneck costs you n time, like 2n time more precisely, but n time. So it's n square, n times n basically. Number of bottlenecks times how much time does each bottleneck takes. Okay, so people are more or less everyone is clear with the n square algorithm. That's good. Between the two bottlenecks, we have to include 500. Yeah. So here actually, yeah, nice catch. Here actually there was a 6,500 inside, because every x has a x, 500 point present. But it doesn't matter. I mean, you still just added n more dummy points, right? So it doesn't matter. To the complexity, it doesn't matter. You get that, right? Like it's still n squared slow. Now, okay. So when we fix a bottleneck, now I'll try to like define some kind of data structure to get you the idea of stacks. Like not a data structure, more like a C++ struct. C++ struct. The idea is you have a bottleneck, right? In this case, it was this guy, x equal 4, y equal 4. So we just keep bottleneck underscore height. So this is 4. Now there is a right x, which is how much? So when we are this, the right endpoint comes at 8. So it should be 8. And the left endpoint comes at 1. So there's this entire structure. If we have this structure, right, let's name the structure something. Let's name this rectangle. No, let's name this, I don't know, candidate. Okay. So we have, like, if you're given all these three informations as your input, like what's the bottleneck height, how much is the right x, how much is the left x, then you can calculate the rectangle, right? You can calculate the area. It's 8 minus 1 times 4. It's r minus l times 4 times height, right? And how many candidates you have? You have n candidates, right? Now, the idea of the stack solution is that, okay, initially we know the bottleneck heights of every guy, but we don't know this thing and this thing. Finding these two things are hard. Like finding the right coordinate and finding the left coordinate is hard. So what we'll do is, using stack solution, we'll first find the right coordinates. So I'll give you an example. Let's say there is this candidate C1, there is this candidate C2, there is this candidate C3, so on. Okay, up till Cn. All of them know their bottleneck. Okay, all of them know their bottleneck. None of them know their right x. None of them know. And none of them knows their left x also. If everyone knows their right x and left x, we are done, right? We can just calculate these areas and take the max. Everyone gets this. But we don't know the rights and the lefts. And to calculate them naively is basically saying we are doing n square. If we calculated them using the old method that we showed here, that's basically slow. So our solution idea is use a stack algorithm, which I'll explain later, but use a stack algorithm, which works in order n to calculate all right underscore x's. So once we use the stack algorithm, we'll know this thing, the right x. We'll know the right x. For every guy, we'll know what the right x is. Okay. And for every guy, we'll also know what's the left x. So we won't know them in, like, it might happen that you don't know them immediately for everyone. Okay. In this method, what the difference is, in this method, for C1, you'll know everything at once. In the old method, for C1, you got to know everything at once. You ran the algorithm on C1, and then you got to know the right side and the left side together. And then you ran the algorithm on C2, and you got to know the right side and the left side together. What I'm saying is, let's try to do something differently. We obviously know the bottlenecks, that's common sense. And for the right side and the left side, let's calculate them on the go. Let's calculate all the right sides first and all the left sides first. And then once we have everything, then calculate the areas. It's just a slight different method of calculation. That's it. We are still calculating the same values. We are still calculating the right points, left points. It's just I'm saying reorder the calculation. Like do it in a slightly different order. Instead of finishing C1 completely and then finishing C2 and then finishing C3, I'm saying do them simultaneously. Some sort of simultaneous thing. I'll explain in stack algo what I'm meaning exactly. But just get that you can reorder your calculations and it'll still work out. Okay. So now for the stack algorithm, okay, let's see how many people are actually online, because the session is actually getting extended by quite a lot. Okay, 26 people are still online. Okay. Do you guys want a 5 minutes break? If not, I can continue. If you guys want to get water or something, then we can have a break of 5 minutes. In case people are interested to get a break, just put it on the chat. Yeah. Okay, not much interest in having the break, so let's continue. Yeah. So, okay, for the stack algo, the idea will be something of this sort. Let's consider a simpler question first to get the idea across. Let's say I have this question. You have an array A. Let's say you have this array 7, 6, 10, 3, 5, 9. Okay. For each guy, try to find, for each element, try to find the right element which is immediately smaller to it. So what I'm saying is your right X array should look like this. For 7, what's the right element? It's 6. That is, 6 is the first element which is smaller than 7. For 6, what is the right element? It's 3. That is, 3 is the first element which is smaller than 6 to the right of 6. Okay. For 10, what is the first element which is smaller than 10 to the right of 10? 3. For 3, what is the first element? Let's say there is a 0 here. Then it's 0, right? For 5, it is 0 again. For 9, it's 0. Does everyone get this sub problem that I'm trying to solve? Just consider this problem independent of the previous, like of the stack question. For now, consider it independent. I'll show you how to combine this. But like the question is given an array, which is like this thing, 7, 6, 10, 3, 5, 9, 0. Let's say this is the array, 7, 6, 10, 3, 5, 9, 0. Okay. You want to find the right X array. And this array is defined as following. For 7, try to find the first guy to the right of 7 who's smaller than him. So that's 6. So that's why this value is 6. Now, for 6, try to find the rightmost guy. Try to find the immediately right guy to the 6 who's smaller than 6. So you go one step ahead, 10. 10 is not smaller than 6. So you go one step ahead more, 3. 3 smaller than 6. So you put 3 here. Then for 10, you try to find the immediately right guy to 10 who's smaller than him, which is 3. So you put 3 here. For 3, who is the immediately right guy to 3 who's smaller than him? So you go 5, then you go 9, then you go 0. So you find 0, so you put 0 here, and so on. Does everyone get this? Or should I repeat it again? Like, what does right X denote? So I'll write this here. Right Xi denotes value immediately to the right of AI that is smaller than AI. Okay, so for 7, the immediately value to the right of 7 that's smaller than 7 is 6. For 6, the immediately value that's smaller than 6 to the right of 6 is 3, and so on. Yes, so Shubham is right that this should take n square to solve. I mean, the naive algorithm is n square, which is basically fix your I and then try to calculate right xi, right? Fix your 7 and then try to calculate what's the right x of 7, and so on. The interesting thing is this thing can be done in ON. So first we'll show how to do this in ON. If there's a case that there is no smaller element to the right, okay, I mean, you can just put -1 or something. Just put a -1. Like for this, let's say for the last guy 0, there is no guy to the left, right? So just put -1. I mean, that's a question I am defining, so I can define it anyways. Now, okay, the naive algorithm is n square. You guys can think about the n square algorithm. It's pretty simple. But what we are interested in is an ON algorithm. So I'll show you how to solve this in ON. Once we have got this, then tackling the previous question becomes much simpler. Okay. So to solve this question in ON, what you need to do is, so you use a stack, let's label it S, and you have this array, right? 7, 6, 10, 3, 5, 9, 0. You first put in 7, then you put in 6. Now, when you're putting in 6, you realize that the stack's top 7 is actually bigger than 6. So you say, pop 7 out from the stack. Okay, let's think about the stack more like a stack. Let's not think about it like an array. Let's think about it like an actual stack. So let's put the stack here. Okay, let's put 7 here at stack's bottom. Right now, when you see 6, you're going to insert 6. But before inserting 6, you'll say, what's the top of the stack? The top of the stack is 7. You'll say 7 is bigger than 6. So pop it out. So pop out 7. Once you've popped out 7, you're basically saying remove it. And then you're pushing in 6. So basically now 6 is the top. And 7 is removed. When you removed 7, you would have also updated that the answer for 7 is 6. You would have updated at that time only that the answer for 7 is 6. Now, after putting in 6, you'll see 10. So you'll put in 10. When you're putting in 10, you'll check, is the top of the stack bigger or smaller than 10? So the top of the stack is 6. 6 is less than 10. So you can put it normally. Okay. The idea being this. So when I'm using the stack, my intuition is this. Initially, we had a guy at height 7. Like, think about the rectangles question. You can think of it like this. Oh, sorry. We had a guy at height 7. Okay, let's say this is the height bar. This is 7. This is height 10. This is height 6. So on. We had a guy at height 7. Now, when we got a new point at height 6, we knew that this guy's limit is here. That this guy ends here. His right coordinate ends here. We knew that, right? When we saw a new point at 6 to the right of it. Let's say this guy's x is something. I don't care, honestly. Like this guy's x is 1. This guy's x is 2. So on. We don't care about the x coordinates. We only care about the y coordinates right now. So don't think about the x coordinates. Okay. But you got to know that once you pushed in 6, I popped out 7 because I knew the limit of 7 now. That this guy stops here. He can't go beyond this point. He can't go to the right of this point. Now after 6, when I saw 10, I didn't pop out 6 because I know 6 can go beyond this point. 6 doesn't need to stop here. 6 can go afterwards also. So when 6 goes 10, then it sees 3. 3 is actually somewhere here, right? So the next point comes somewhere here. Now, after putting in 3, we need to pop out 6. We even need to pop out 10. So initially the stack was 7. Then we pushed in 6. So it got popped out 6. Then we pushed in 10. Now we'll see 3. And we'll pop out both these guys. Because 3 is actually bottlenecking both these guys. That's the idea. That when you see 3, you realize, oh, okay, so 3 is bottlenecking 10, so pop it out. 3 is bottlenecking 6 as well, so pop that guy also. You can see there is some similarity to the DQ question here, that we are popping out things. Also realize that there is an invariant here also, similar to the invariant we had in DQ. The invariant here is stack from top to bottom is decreasing. You have this invariant, that the stack from top to bottom is always decreasing. So initially, what did you have? Initially, you just has a 7. So this invariant is maintained. Now 6 comes up. Like now 6 to 7, this is not decreasing, right? Because 6 is smaller. So you need to pop out 7 and then you put in 6. Now when you get 10, this is decreasing because 10 is bigger than 6. So this is decreasing nature. Then when you see 3, you realize that this is not decreasing nature. So you keep popping out things till the time you get that decreasing nature. So you pop out 10, you pop out 6, and then you put in 3 because it's empty after that. Had there been an element, let's treat a slightly different test case where instead of 6, this was actually 1. Okay, so first you insert 7, then you see 1, so you pop out 7 and put 1. Then you see 10, you put in 10. Now when you're putting in 3, you'll only pop out 10. You won't pop out 1 because you have the invariant that 3 is less than 1. 3 is greater than 1. Decreasing invariant. Stack from top to bottom is decreasing. Right? And notice whenever you're popping things out. So in here, when I was popping out 7, like when I had 7 inside and then I saw 1, when I was popping out 7, I updated its right x to 1 at that time only. I said in my candidate 1, put its right x. That is, the right x of 7 is 1. Or basically here, 7's right x is 6. Instead of 6, we have a 1 here. So it becomes 1. Put it right now only. Now after 1, when you see 10, you just push it in. When you see 3, you're going to pop out 10, right? When you're going to pop out 10, update its right x to 3. Which is basically this thing, this value. This value. Notice this, what does this value refer to? What's the right x of 10? That is, which is the value that's bounding 10 to the right of it, which is 3. So you update it here only. And I messed it up slightly. So actually, let's just take the case of 6 only. One will actually mess things up a lot because this array is built using 6. So I'll have to treat like a different case. So let's say there was 6 here, 7 here, and then 6 came, and then 10 came. Now right x of this is 3 when 3 is being inserted, right? And this is popped. We see 6. 6 is still breaking the invariant. The invariant being that it should be decreasing. But 3 is actually smaller than 6. So it's breaking the invariant. So we need to pop out 6 also. When we are popping out 6, we'll update its right x also. And put it as 3 because 3 is the thing that's being inserted. So notice I got 6 here, I got 3 here, I got 3 here. I got them at different order. I didn't get in left to right order. I got this guy first, then I got this guy, and then I got this guy. So even though I got them in like slightly different order, I did get those correct values. Is this thing clear? Like the algorithm will keep on running, but the idea that you're inserting things in a stack, you're trying to maintain this invariant, and whenever you're popping out stuff, you're updating. So if you're popping out x because of inserting y, what does that mean? That means y is smaller than x, right? And you'll set right x of x as y when you're popping out. Okay, repeat the last thing, please. Yeah. So you're maintaining this invariant. I'll go through this example once more just to get people clarified. I don't think we'll have time enough to implement this entire thing. So I'll just probably like share some code or like maybe in some future session, or we can have an optional thing. But yeah, so we have a stack, and first we inserted 7, then we inserted 6. But when we were inserting 6, we realized, oh, the invariant is broken. So we need to pop it out. When we are popping it out, we use this thing that is say, update its right x, update its right. So at 7, we'll say set its right to 6. Now we'll insert in 6. Now we'll insert in 10. Now when we are trying to insert in 3, we'll again break the invariant. So we'll say, okay, pop out 10. When we are popping out 10, we'll say change its right to 3. Here, popping out x because of inserting y, then we should change right x to y. So we'll say his right is 3. And we'll pop him out. Then we'll see 6 and we'll say, okay, we are popping this guy also out because the invariant is still broken. The invariant still doesn't hold true. So we are popping out 6 also. And we'll set his right to 3 also. And then we'll insert 3 and so on. Now notice you've actually got the correct right x's here. You've got the right x 6 for 7. You've got the right x 3 for 6. You've got the right x 3 for 10, which is same as these 3 guys. And you'll keep on insert. Let's say after 3, the next point is 5. Right? So you'll put in 5 and the invariant is not broken. Now the next guy is 9. You'll put in 9 and the invariant is not broken. Now the next guy is 0. Now when you're trying to insert 0, you'll realize that the invariant is getting broken. So you'll first delete 9, update its right guy to 0 and pop him out. Then you'll delete 5, update its right guy to 0 and pop him out. Then you'll remove 3, update its right guy to 0 and pop it out. Then you'll insert 0. So notice this entire thing that's being constructed here. The right x's. This guy's right x was 6, this guy's right x was 3, this guy's right x was 3. And these guys right x was 0, 0, 0. Notice these right x's match these that we were trying to construct. Right? Okay, so what if no smaller guy came while picking up element from array? Nice question. So that's why we can think of adding a dummy. Like I added a 0 here just to pop out everything of the array. You can think of it like you'll always have at the end of the array, you'll always have a -1. You can think of it like this. So that this guy will make sure that whatever is present in the stack at the last step gets popped out, because -1 will be smaller than every guy. So he'll just pop up, keep on popping out. Now, do you notice the similarity between this thing and how we are bounding the stack? Like these right x's actually denote the limit of the bottlenecks, the right side limit of the bottlenecks. Like for 7, this is the bottleneck. For 6, this is the bottleneck. 3, the guy 3. For 10 also, this is the bottleneck. For guy 3, probably 0 is the bottleneck. For guy 5, probably 0 is the bottleneck. For 9th guy, 0 is the bottleneck. and we got those things in the right X. So actually recovering right X in order n is good enough. We've actually got the right bounds. Any doubts here? So just remember these two things, like these two are the important things I would say. Maintaining the invariant in the stack, which is that top to bottom is decreasing. And whenever you're popping out a guy X, because you're inserting Y, then you need to update the right limit for X as Y. So like these two are the key things in the implementation. So we got how to get right X, right? And okay, actually it will be similar to DQ in some sense that you'll actually have pairs inside. Like I'm not doing the implementation right now because I don't think we have time enough for the implementation of this question. Because it's going to be a slightly tedious implementation. Like maybe we can have another session for it. Or I don't know, maybe if a lot of people are interested in actually doing the implementation, then we can do it. But the idea being that there will actually be pairs here, and the first element would be the X, the second element would be the Y of the pair. And yeah, you'll have pairs, and this thing will actually have the X coordinate. So right now I was trying to denote right X as 6, but it shouldn't be 6 actually. It should be the X coordinate of this thing. So the X coordinate of 6 might be like X equal 8, or like let's say X equal 3. So the right X should actually be 3, because notice in the candidate we wanted the bottleneck, the height, and we wanted what's the right X coordinate, what's the left X coordinate. We don't want the Y's, we only want the X's, right? And the 6 is actually the Y. So we actually need a pair here. I was just using values because it was much simpler to explain. If I had used pairs, it would have got confusing that what's the first, what's the second. But like, yeah, the idea is that you actually need to have pairs here where these guys are the Y's. The 7 is a Y, the 6 is a Y, the 10 is a Y. These are the Y coordinates, and you'll also have the X coordinates. And your right X will actually be the X coordinates. So let's say this 6 has the X coordinate of X2. So this thing will actually be X2. Let's say this 3 has the X coordinate as X4. So this value will be X4, this value will be X4, and so on. So the right X is actually the right X is actually the X coordinates of those limits. And you can get those X coordinates using the stack solution. Yeah, like Krishna is correct. Like you can check the already existing implementations, or even I can show brief implementation, but yeah. I mean, okay, I'll write a pseudocode quickly, just to give the people an idea of like how it will look. Like probably my code won't be entirely correct, obviously. So let's say we have an 1503.6. Okay, and then we have like this. I won't compile this code even. Like I don't think it'll be good enough to be actually compilable. So we are taking in all the points. Just get through the broad idea. So what we'll do is we'll say okay. So for each, like what is Vx trying to denote as it's a vector in this thing. So it's a array of vectors. So right, I'm first inserting all the 500 dummy elements, like all the 500s, the top guys. I'll also insert v0 dot pushback 0. Okay, and also insert v 10 to the 5 dot pushback 0. So these are basically the dummy elements that are inserted, right? And these are the actual elements that are inserted. So for each X, I'm inserting some Ys for that X, whichever points come, okay? And then I'll also do something of this sort. So I'll sort them, right? Now, let's say like the broad code will look something like this. You'll have a stack and you'll say, okay, we'll start pushing things from the left to the right. So for auto Y, so I'm basically iterating over all the points, and then I say push what point I'm trying to push. I'm trying to push X comma Y. Okay. And the way this works out is like the push will look something of this sort. Okay, so let's just code push here only. So while S is not empty, if S dot top dot, okay, so S dot top is the stack stop guy. If that's top, if the stack stop, okay, we want the invariant, right? The descending invariant. So if the stack stop dot second, because I'm comparing the Ys, is less than, sorry, is greater than my Y, which is basically Y, then I say S dot pop. This is slightly confusing. I'm saying the stack stops Y coordinate. The dot second means Y. Here I'm saying that the first thing is X, the second thing is Y. So if the stack stops Y coordinate is bigger than my Y coordinate, let's say the stack is looking like this, 5, 3. And let's say we are inserting, I don't know, 7, 2. Then we'll say the stack stop second, which is 3, is greater than RY. So we need to pop him out. So we'll pop him out. Okay. Before popping him out, we'll say right of S dot top dot. So that's why the implementation is slightly complicated. We need another integer to denote. So okay, I wrote this very quickly. So I don't know if you guys can get the hang easily. But I'll explain this. Yeah, I should explain this. Give me a moment. So, okay. So each X comma Y coordinate will also have an ID. I want an ID also, right? So each X comma Y coordinate needs to have an ID. That is, which point is it? Is it the first point? Is it the second point? Which point am I talking about? So initially all the IDs are set to -1. Okay. Once I sort all the guys, then what I'll do is I'll set counter to 0 and I will loop over all the guys and say v dot second equal plus counter. So here I'm just setting all the IDs in this code. Okay, I'm not sure how much you guys are familiar with STL. You can ask me trivial questions. Like this is, okay, so Shruti is asking, this will be n log n, right? Yes, because I'm doing the sort here, correct. But I don't think you need the sort here necessarily. Example, you can use counting sort because Y's go only till 500. But yes, otherwise you're correct. You need all the points sorted by their x's. So you can realize that, you can notice that for sorting by x's, I'm actually doing a counting sort. Whenever I take in a x comma y, I actually put it in the xth vector. So it's like I have sorted all the points by x using an implicit counting sort. To sort them by y, I'm actually calling the sort function. To sort them by y within each x, I'm calling sort function. Right? So I first give them all of them IDs. Then I say my stack's first element will be So I'm saying s dot first will be the ID, s dot second dot first will be x, s dot second will be y. Okay. Now I'll compare the y. So this thing will actually look something like this more. Like 1 will be the ID and 5, 3 will be the thing. And I'm trying to insert maybe say 2, 7, 2. Okay. And this thing will actually be v, ID. And here I'll say right of this thing is the ID. That is, this guy's bottleneck is done by this point, which is extracted here, the second element of the pair. And I'll keep on popping. Sorry. Otherwise, I'll break here. And after all the popping, I'll push this guy inside. How do I push this guy inside? His ID, his x, y. Like that will be the broad pseudocode. I mean, okay, this thing shows an error right now because this syntax is supported in C++ 17 and not C++ 11. And my compiler is not set for C++ 17 right now. And yeah, this array we haven't defined, so we can just define this array. And then this will basically be write access. Like if you do something of this sort. So after doing this, we can also do a counter equal I, b dot first. So basically I'm saying, so because I'm inserting some dummy elements, that's why it's 2 times n, right? And here I'm saying a counter, that is this ID's guy, x coordinate is I and y coordinate is v dot first. This I is actually the x coordinate. Is it needed to sort by y's for each x? It's not really needed, Shruti. I think you can get away without sorting. I wanted to sort just because I wanted to give them IDs, and I thought it would be more systematic. Although I'm confident that it's not needed. But yeah, I just did it for my because I was thinking it'll be simpler to know that the IDs are ascending in y. And once you've given them IDs, now here you can actually do, instead of ID, you can put AID dot first. Oh, sorry. A is already defined, right? No, A is not defined. Yeah. So here AID dot first is actually referring to this ID's x coordinate. Like whichever point this ID is referring to, that guy's x coordinate. I'm not I'm 100% sure this code doesn't work right out of the box, but that's the broad idea to find the rights. And you can find the lefts similarly. Like just now I found the rights. To find the lefts, the main difference would be your x will start from here and it will go till it'll just go decreasing. That's it. More or less the remaining thing will remain the same. Yeah, that's pretty much the difference between rights and lefts. The way you iterate over the points. Instead of going from left to right, you'll go from right to left. So notice I'm updating the lefts and the rights when I'm popping guys. So when I'm popping a guy, I update his left or right, and so on. Does everyone get the broad idea? It's similar to the DQ question in some sense, that whenever you're popping guys, you're putting some information on them. That, okay, now they know their right point. And whenever you're popping guys here, now they know their left points. And you keep on popping till the time the invariant becomes true, which is that the y coordinate shouldn't be bigger than your coordinate. And once it's smaller, then you get that descending property, and that's why you break. And the syntactical sugar that I'm using is mainly ranged based loops. So this is a range based loop. If you want to iterate over a vector vi, then you can use this kind of syntax, auto v colon vi. So here v will actually get all the values for vi. It'll get, so v in the first iteration will be vi0. In the second iteration, it will be vi1, and so on. And here the syntactical sugar was that y will be vi0 dot first. and ID will be vi0 dot second in the first iteration. In the next iteration, it will be vi0 dot, sorry, vi1 dot first, and ID will be vi1 dot second, and so that's the syntactical sugar. Like basically, this is a very easy way to write what you are trying to do. That is, assign the first value of the pair to y and assign the second value to y. Yeah, that's the broad pseudocode. I mean, I won't write the exact details, but yeah, that's how the thing looks. We can maybe have another session, or maybe I can just like, yeah, sitting at home, maybe record myself, or if I can get this thing working, I can just upload this code. So any doubts regarding this question? I mean, it's a pretty long question and tedious question, but like, yeah. The idea of using stacks and like basically the bottleneck issue, like that we are creating bottlenecks, and then we are, for each bottleneck, we are making a right X and left X, and creating the right X's together is ON because of the stack technique, and creating the left X's together because of the stack technique is also order on. So let's end this session because okay, Vishnu is asking, instead of taking stack pair, some people are taking an array and compare X and Y values as soon as they take input. Instead of taking stack pairs. I don't get the idea exactly. You can probably check on the submission and see if they're only ACing subtask 1. I guess those kind of solutions will only AC subtask 1. Like you do need a stack or a binary search or something or that sort to get an nlog in our order and solution. Yeah. Yep, you can't go beyond like if you're not maintaining a stack or a vector of all the XYs, then you can't get the nlog n or anything. I mean, stack was just one method of us doing it, but like also everyone please share this feedback form that we have. Oh, sorry.